SwayamPrabha. Digital India. Educated India.
Please take this plug flow assumption. You write plug flow assumption. This I have taken from Denby book, the original person, in his own words. We will write that, and then you can just, I think whatever you have discussed it is here, but nothing like you have a para on that, so that anytime you can refer. Okay. Plug flow assumptions. 1, over any cross section normal to the fluid motion, over any cross section normal to the fluid motion, the mass flow rate and the fluid properties in the bracket, fluid properties in the bracket, pressure, temperature and composition, pressure, temperature and composition, close the bracket, are uniform, are uniform. Number 2, there is negligible diffusion relative to the bulk flow. Good. Right, next para, that is point 1 and point 2. Next para is, under assumption 1, the residence time of all the fluid elements in the reactor is same, and all these fluid elements pass through the same sequence of pressure, temperature and concentration changes. Okay, right, next para. Under assumption 2, the molecules of reactants and products do not diffuse from one element to another element of fluid. Okay. Then write another para. The above 2 restrictions allow the conversion in each element same. What is assumption 1? In your normal terminology, what is assumption 1?
Flat velocity profile.
Is it flat velocity profile? Rajeshwari? Yeah. Infinite mixing in the radial direction is assumption 1. Straight away, because you are having pressure, temperature and composition same at any cross section. No? So, that means you have infinite mixing in the, that is what our assumption is. Most of the time we tell that. What is second assumption? Can we? Axial mixing equal to 0. Okay. So, under assumption 2, what I try to tell was that first assume that all particles have uniform residence time, then the other 2 automatically come. He has given the other way, he first defined those 2, then said that under assumption 1 all residence times must be same. Okay. Under assumption 2 there is no diffusion, that means there is no axial mixing, all that, but axial mixing only, radial mixing must be there, otherwise you do not get uniform concentration and temperature. Very good. Yeah. So, now I will just give you one exercise, very simple exercise for you to do and then keep in your notebooks, and when I ask separate test, probably you have to derive this. Show for unsteady state plug flow reactor minus dou F by dou V equal to minus R A plus dou C A by dou T. That is the equation which you have to derive. Okay. That means you have to write the material balance, it is only isothermal condition. Okay. So, what is entering, what is leaving, what is accumulation, what is reaction, all 4 terms, right. Earlier we have taken only all 3 except accumulation. Now, you have to also put accumulation, and then you will get dou C A by dou T, but you have to write clearly what is the element you have taken, what is entering in the element, leaving in the element, accumulating in the element, reacting in the element, put all 4, cancel out whatever is there and arrange that equation in that format. Okay. Good. Now, we will go for mixed flow reactor. Okay. So, the this name mixed flow reactor Levenspiel uses very widely. So, that is why we also use that, but there are also other names for this. Okay. Mixed flow reactor, you should have heard of CSTR. Yeah, back mix reactor. So, this is CSTR. What is the meaning of CSTR? Okay. So, what is the difference between this and then batch reactor, where you are also continuously stirring, that is also a reactor, that is also a tank. Huh? Okay. So, how do we know that? Because for batch reactor also it is same, continuous stirred tank reactor. There is continuous stirring, correct, no? And it is a tank reactor, it is a tank and reactor. So, yeah. So, what we have to remember here is that continuous with respect to what? Flow. So, they write there continuous flow stirred tank reactor, they put F here, CFSTR, continuous flow stirred tank reactor to specify. But I think so many words we do not have patience to use. So, that is why we say CSTR, that continuous is with respect to, yes, good. So, I think other reactor also BMR, back mix reactor. Continuous stirred tank is straightforward, that is what is happening. Flow is continuous, there is stirring, it is a tank and it is a reactor. So, continuous stirred tank reactor. Good. Then why do you call it as back mix reactor? You see, all these things you have to think. You should have asked 2 years, 4 years back. No, I think third year only it comes, no, BTech third year only reaction engineering. You should have asked the teacher in that class, sir, why are you, for example, this C refers to what? Is it a continuous stirring or continuous flow? Continuous stirring means it is equivalent to batch reactor. They are also continuous stirring, here also continuous stirring. So, BMR means if you would have told BMR, then you could ask what is this BMR? Back mix. What do you mean back mix? So, that means it is mixing back. Okay, I think this name has also come from the two origins. Okay, one is that with respect to plug flow reactor itself, axial mixing is also called back mixing. Correct, no? It is going forward again coming back, going forward again coming back. Okay. So, that means that is what some kind of back mixing is happening, but that is limited to only small axial direction, but small region, right. But in CSTR, when you say back mixing, let me also draw now the figure, normally what we draw for CSTR. Okay. So, this is the one, we will show that it is continuously entering, continuously leaving, and if it is non-isothermal reactor, you will also put. Okay. So, here maybe anywhere you can introduce. So, I will introduce here coolant entering, coolant leaving, that is the coolant. Okay. So, here you will have same thing, FA naught, V naught, CA naught, XA naught. So, here you have FAF, CAF, VF, XAF. Okay. So, we are talking about back mixing. So, the idea here is that you are continuously feeding this reactants, and then they come, they mix here, and then some of these molecules which have just entered because of mixing, some of them may about to leave. So, this is the outlet about to leave, but when they are about to leave because of mixing, because mixing means chaos. Okay. The definition of mixing is that any particle will stay in the reactor, and the probability of the probability of leaving a molecule, the probability is same for all the molecules when they are about to leave. The probability, I think it is a confusing definition, mixing. Okay. So, that some of these things we do not have real meanings, like I told you again love. Okay. Mixing, we say mixing, we say perfect mixing. What do you mean by perfect mixing? When do you say that you have perfect mixing? Yeah, when do you say that you have complete mixing? She is saying when I say perfect mixing, complete mixing. Okay. So now tell me, when do you say you have complete mixing?
Each of the particles should pass.
What level? See, every concentration may be at what level we are talking? Huh?
The desired level of homogeneity.
Yeah, what is that level? Homogeneity, how do you define again? Really? Because you should think all this, no? See, even if you don't have perfect mixing also, some molecules will collide with some molecules. Okay, so that's why. Huh?
Say one molecule, if it collides with all the molecules in the reactor, we can call it perfect mixing.
Now, how can you expect that one molecule collide all molecules? My God, it is a kabaddi versus 1,000 people versus one guy. They will pull him out. I say. So one molecule we cannot know. Yeah. See, the definition there is probability for this molecule is maximum when it is colliding with any other molecule. That is what the probability of this molecule colliding with any other molecule, not all molecules. So any other molecule means what are you trying to say? That molecule may be here or here or here or here or here or here. The colliding molecule may be coming here. Okay. So the probability of that molecule colliding any molecule is same. Like that for every molecule, the probability is same. Any one molecule you take. So the probability of that molecule colliding with any molecule inside the system is same, right? And we are talking about the homogeneity. When you said homogeneity, homogeneity at molecular level, that is the real definition. What is the size of molecules? You can't even measure. I mean, you can't definitely not, you can't see it, and you need very sophisticated instrumentation to look at the particular molecule. Now we have beautiful instruments. Okay. So that is what is the definition of perfect mixing, and back mixing is that molecule which is about to leave because of that chaos, again it may be brought back even to the feed. That is what is back mixing. The fellow who is about to go out, okay, like you joined 4 years back for BTech, and then you now about to leave, okay, in the final year, you are now asked again to go and join first year, first semester, first class. Okay, that can happen in perfect mixing. Okay, that is why in all academic system, that 4 years, if every one of you pass, what is the system you describe? PFR, plug flow. All of you, really, all of you are spending exactly same time, 4 years. All of you join on one day, all of you leave on the convocation day, over. Exactly, in between what you do is not matter. Doesn't matter, but the leaving, entry and leaving is exactly same. That is what is plug flow. But in reality, what kind of flow you expect? Axial mixing. Why? Some people may take 6 years, some people may take 4 years only, because you don't have that system. But in IIT Madras, our system, credit system, theoretically one can go in 3.5 years also, because it is electives. Core courses are compulsory for everyone, and if you allow them, now I think we put a maximum of 6 courses here, right? If you allow them, if you are very good, you can take even 8 courses in a semester. So that means you are able to complete some more courses before others, so you can go earlier. I think that in USA many universities they have that credit system. There it is axial dispersion. The average time is 4, right? So some people may go in 3.5 years. Okay, 3 years may be too ambitious, but I think 3.5 years they may go. Then some people may go, we don't know that time, infinite time also they take, because that means they never got the degree. That is what it happens. So that means it has got long tail, we say, correct? No time. The infinite also still is not coming out. So he is still in the BTech classes. So that is why that back mixing is that example where you have completed almost everything, and now you are brought back and then put again first year. So that is what happens in the mixing. When the molecule is about to leave, it can back mix with the molecules which are just entering. That is the meaning. When you are asked to sit down in again first year, you are now joining the molecules which have just now entered. Those students would have just then joined, you are also joining them. That is what is the meaning of back mixing. You see how much meaning is there in each and everything. I mean, as students, you have to start questioning. I say, even now you can start questioning. You should make the teacher's life hell. Really, if all of you are asking questions, my God, we will become very sharp. I say, really, we will become very sharp. I know those. I mean, those people who hands off, then we cannot do anything with them. You ask and I will say something, and then we will go. We will forget. But many people are not like that. When a student asks, it is also a challenge to the faculty member to learn if he does not know immediately, and to request others to explain, and also he will learn and come and teach you, so that he is also learning. That is why teachers are lifelong learners. You will stop if you go for job, but we never stop learning, really. So, but I think you can aid them to learn more with your questions. Any question, there is no stupid question, only there is stupid answer. Okay? Question is not at all stupid anytime, I tell you, because I told you, no, simply, okay, how many noses a person has, human being has. Okay? It is not a stupid question, because you have never seen a human being, so you don't know whether there is one nose or 10 noses. Okay? Or legs, how many legs a human being has. You would have never seen a person. Like there is a horse in that Avatar movie, right? Yeah, that horse. What is the speciality of that horse?
Unicorn.
I don't think it breathes with the nose. It breathes something here. I think there are some 2 holes here, I think, if I remember correctly. Yeah. So, some change. Okay. So, that kind of horse, okay, where is the nose for that horse means you cannot tell, because nose is here. I mean, that is what I remember vaguely. Now, I do not remember whether it is, but here these flaps will move up and down. That is what I have seen. Here some flaps are there. So, that is why I am just giving an example that the question, you should not be afraid in asking any question. So, at the maximum what will happen if you ask a wrong question? There is no wrong question, I am telling, but in the heads of your own classmates, okay. So, you may be afraid that if I ask this question, my classmates will laugh at me. So, when someone laughs, what will happen? Nothing will happen, only his teeth will be seen. Correct? No, you see, Pooja laughed and the teeth I can see. It is very difficult to laugh without showing the teeth. No? How can you laugh? I said, try. It is very difficult to laugh, no, without. Yeah. So, what will happen maximum? Some white material will come, more light is reflected, the room will become more bright. That is all. So, nothing will happen to you. Okay? Nothing will really happen. That is why I encourage you to ask any question the moment you have any doubt. Any doubt, I tell you. But you are not doing that. I think every class I tell, but I think because they are not asking, then I will ask the questions and I will also answer the questions. So, that is what is happening in most of the classes. I think you should do that. Okay, good. So, in the perfect mixing, you know that simplest assumption is that we have perfect mixing. Now, the question is how do you define perfect mixing? So, we are trying to say that this mixing is at molecular level. If at molecular level, if you can see the homogeneity, homogeneity means you take a small amount and then see all the molecules are uniformly present there, and you take in another corner another small lump and then see again there, you will also get the same number composition like any other place in the reactor. Okay? It is very simple to just only keep in your mind that is the meaning of perfect mixing. Okay? Good. So, now we can also tell something connected with this, what is called residence time distribution. By the way, what is the residence time distribution in plug flow reactor? Residence time distribution. The moment we say distribution, our minds 50% will be closed. Distribution, I am simply asking what is the residence time distribution in plug flow. So, then what do you say? Straight line is not distribution. I am just asking what is the residence time distribution. In words you can tell. Okay. So, then what do you say? Residence time distribution is 0. Same you cannot say. Distribution is not same. Distribution means there is a distribution. 10 seconds means exactly everything is 10 seconds. What is the distribution? Distribution means you should have 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That is the distribution. Like you have here distribution of ages. All of you are not exactly 21. Correct, no? All of you, if you have exactly 21, in this world also, this group has plug flow. That means 21 years back exactly you are born. if the date of birth also is same for all the people. But in this room we have distribution from almost 21 to 65 because I am also in this room, I say. I cannot eliminate myself. Okay. Yeah, you see that is the distribution. One guy with 65 years and many people with 20. There are some people with 30 years. There are some people, maybe external registration people would have been around 32, 33, and I don't expect 50, 40 like that generally. So I think it goes peak around 30, 35, not 35, around 30 or maybe 28, and then long tail, this fellow here 65. Okay, that is the distribution. Okay, so that kind of distribution is 0 for PFR. So that is why sometimes we also ask, tell me a reactor where RTD equal to 0 PFR. Okay, now we see this because of mixing, what is happening to RTD here, residence time distribution. Oh, RTD means I think this is RTD, we use residence time distribution. That means when you look at the outlet, how the particles are coming, whether some particles are coming slightly earlier, if the mean residence time is 10 minutes in this case, or some particles are coming to 20 minutes, 30 minutes, or all the particles are coming at 10 minutes only. Okay? If you say that all particles are coming only exactly at the 10th minute, then I have the plug flow, that all that over 4 classes we have taken. Now we are talking about mixed flow. In this case, how the molecules come out, because molecules are very easy, very difficult to imagine. So now let us imagine that these molecules are grouped together, some packets of molecules, and now it is a continuous reactor, and I am now imagining that I have these packets continuously entering and also these packets are continuously leaving, just for the sake now. Okay, just imagine that these packets are continuously entering, continuously leaving. Okay, good. Then we can also imagine afterwards molecules. Then when the let us focus on some 100 molecules or 100 packets, and at time t equal to 0, it is continuously feeding, continuously coming out, right. So at one time I would like to find out what is happening to these 100 packets. Now I just imagine, jadoo, magic. So through magic I will say that let these 100 particles will be red color. So all of them will be suddenly red, right. Now I will try to follow that red color here. According to perfect mixing definition, all these 100 there are many others also, many other packets. These 100 packets only I am concentrating. These 100 packets will be uniformly distributed throughout instantaneously, because that is the meaning of perfect mixing. Okay. So then when you have that immediately uniformly distributed, when they are distributing, because of mixing only they are distributing, one packet may come here and that may suddenly come out, right. There may be another packet which may go to this corner, but still it is mixing well, but it is not able to come, but it is moving here, moving here, moving here, moving here, there. That can happen because of again mixing, mixing, right. So that is why you have the molecules moving inside, but some of them will very quickly come out and some of them may not come out for long time. That means you have the residence time distribution. If I choose that 100 packets, one packet will come in 1 second, another packet may come in 5 seconds, another packet may come in 50 seconds. Okay? The mean residence time is, let us say, 100 seconds for easy imagination, right. And some other packets may come 1000 seconds, after 1000 seconds. So that means if I plot that concentration of particles, because concentration means that moles per unit volume. Okay. If I am able to plot that, then what kind of graph you get? Good. Okay. So now before that we can also, these are the packets with the red color and all that. Now imagine that I have water, so that I can ask you how to plot that graph, concentration versus time. Okay. So I have water and continuously water is entering, water is going out. Then what I did here is that I took my pen, that is red color I have. Okay. So that red color, one maybe 10 drops or 1 drop, suddenly I added. I have a small reactor. maybe 50 ml jar, okay, the beaker. So, continuously I am putting water, continuously water is coming out. So, in this there is stirring, good stirring. Then at one point of time I just put my ink, red ink, one drop. What will happen? It is a perfect mixture. What will happen to this ink? Instantaneously completely mixed. Okay. So, then onwards how the color changes inside the reactor or at the outlet. Just before adding, what is the color? Colorless. Okay. At time t equal to 0, I have added that color. So, my time t equal to 0 will start here. This is concentration. Okay. Right. At time t, this is 0. At time t equal to 0, I added. Previously it is only white. Instantaneously it is distributed, mixed very well. So, then what is the definition of perfect mixing? Other extension of perfect mixing also is, when you have this assumption, the contents inside and also contents in the outlet both are must be same, right. The moment you mix it, this color also will immediately reflect in the outlet. Okay. Yeah, this is where I am measuring now, that concentration in the outlet, not somewhere inside, in the outlet. So, now tell me how the concentration, whether the concentration increases or decreases. First of all, concentration, why it should decrease? Yeah, Abdul has another idea. Concentration decreases or increases, there are only two options. Huh? No, but Abdul says it is increasing.
It will increase and then decrease.
Yeah, why it is increasing and decreasing?
More and more water will be added, then the
Yeah, when more and more water is there, more and more it is diluted.
initially the concentration will be high, and then
Why? I mean, at time when it will be high?
after 1 second, like
Why 1 second? I think Sushmita will say 2 seconds. Can you contradict her?
at this
Danya will say 5 seconds. Why do you choose 1 second?
we can shoot even 0 because instantaneous mixing. So
Yeah,
instantaneous.
it is only at 0th time you have the maximum concentration, because you are not adding concentration later. You are adding the concentration only at time t equal to 0. Afterwards you are stopping. The one drop I have added, that is all. Water is continuously flowing. At that time it is uniformly mixed. So, instead of drop, if I say I added 10 grams of color, 10 grams weight wise, what is the concentration if I have 1 liter? 1 liter reactor I have 10 gram per liter, that is the maximum. Okay. Then continuously water is entering and this will also going out. Yeah, it continuously decreases. Okay. Continuously decreasing means you can draw that lines in infinite number of ways. Correct, no? There is no unique way of decreasing. No, I can draw like this, like this, like this, like this. I can draw like this, like this, like this. Oh no, no increasing. So, like this, anyway, no increase. So, that is why all that is not valid for mixed flow. In mixed flow, it is only valid, mathematically also we can show that, if it is exponentially decreasing. So, this one and then exponentially decreasing. Exponential, okay, I simply write exponential. Okay, right? Okay, good. Now, I know that at time t equal to 0, I have the maximum concentration. In our example, it may be 10 grams per liter. Okay, that at that instant. Afterwards, it may be 9, 8, 6, 7, like that go on. Not 6, 7, 6, 5, 4, 2, 3, till what time it will come? Why infinity?
Of perfect mixing.
Yeah, until all the particles come out, that is a logical answer. But what is the time taken for all the particles to come out? Why you don't know?
possibility that one molecule may stay for the entire time.
Yeah, it depends on actually what is the system you are using for measurement of that concentration. If the color, if you are not able to see beyond certain concentration, eyesight, okay, that means it does not mean that everything has come. Still there may be one or two molecules where you cannot see the color, but still it comes out. So, that is why we say theoretically it is infinity. So, that means now what is the residence time distribution? 0 to, yeah, that is what 0 to, mathematically we can put when with perfect mixing you will get a differential equation where you have exponential e power minus 1 by e t. Okay. So, e power minus t by t bar it will come, right. That we can prove. I mean, when RTD comes, it comes. But I think why I am telling this now at this point of time is that we have a system where residence time distribution equal to 0. You have another system where residence time distribution equal to 0 to infinity. As far as reaction is concerned, which system you think more efficient for a given volume? More efficient means more conversion. Example I gave, adding this color and all that, which we say tracer and all that. So, that example I gave to show that there is residence time distribution in mixed flow, whereas there is no residence time distribution in plug flow. How did we prove that there is no residence time distribution there? You added one disc in the pipe, correct, no, colored disc. Without any disturbance to this disc, exactly it comes out at the end after whatever time you provide, 10 seconds or whatever. So, that means if there is a distribution, that disc should have spread like this. Same thing, sir, why do you say that one drop? Can I put this disc here? You can also put that disc there. I show just arrow here, but actually only if I have one arrow, no fluid can enter, correct, no? It should be a pipe. So, that pipe is something like this, right. So, in this pipe now I will suddenly introduce my disc, correct, no? I can do that. Then that comes here, I will count my time t equal to 0 when it comes here, and assumption is this fellow is not dispersed in that pipe. It is still maintaining as exactly disc only when it comes here. So, here I have the disc. The moment it touches, it enters there, what will happen to this disc? Pieces into pieces. What is the piece size? Molecule. Molecule, because it is perfect mixing we are assuming, right. So, that way it is now made into pieces, and now one piece it will throw out very quickly out of the reactor. So, that may be somewhere here, okay, because concentration you are calling that piece weight divided by volume of the reactor. So, maybe 1 gram would have come, not 1 gram, all that in ideal mixing that will be maximum 10, 8, 9, that will slowly decrease, but in an exponential way. If I say 10, 8, 9 and all that, sorry, 10, 9, 8, 7, it is not linear again, time I am not telling at what time it is coming. So, that is why yeah. So, these timings are all of them will fall on this exponentially, and okay, that disc is into destroyed into pieces, and then that will also come exponential way. Whereas, the same disc there in a plug flow, without any disturbance it will come exactly same time. I think without any same time means exactly same time the entire disc will come. So, that will be t equal to maybe 10 seconds if you t bar equal to 10 seconds if you take at the end of 10 seconds, right. Here I told you for comparison sake, volume of the plug flow reactor, volume of back mix reactor, both are same, 1 liter 1 liter. So, volumetric flow rate is same. What is t bar in these two? T bar is defined as T bar or tau, the constant density system we are talking, volume by volumetric flow rate. Okay? Yeah, I think Arya, this is, I do not know whether you could get this. This is meter cubed divided by meter cubed per second. Okay? So, meter cubed will get cancelled, then you will get seconds. That is why this time is taken as volume by volumetric flow, even though there is a derivation actually for that also. There is a derivation in RTD, I think I can show you that. Okay? That is why we call this one T bar as volume by volumetric flow rate, right? Yeah, based on volumetric flow rate. What do you mean by hydraulic residence time?
Mean residence time, so it actually depends. It may not be this.
Constant density system, I said. I said constant density system. Okay? So, T bar, right? Even in volume expansion, how do you define that tau? Even if it is mixed flow, even if it is plug flow, even if there is change in the moles, right, still we define tau based on initial volume. There both are entering same at the same temperature, same pressure. So, that is why tau will not change. T bar will change, actual flow. Okay, that will come when we are talking about later. Okay, good. So this is what is T bar. See, T bar is same in both here, right? So here T bar is, this is going to 0 to infinity, right? Infinity I cannot show. That is why I think I just only draw something there. So my T bar will be somewhere here. T bar equal to tau. So that means you see now, if I take this is the average residence time. So now beyond average residence time also there are molecules coming till infinity, right? Now I asked you the question that what will happen during reaction, but I asked you a question, no, that given the same volume, okay, so where do you get more conversion? I said efficiency, more conversion. Plug flow you said, why? Because in terms of residence time distribution you can beautifully explain that. That is why I am asking this question. Residence time distribution.
When the molecules come, the conversion is very high initially.
Initially, where is conversion very high? You see, all these cobwebs you have to remove totally, right? Because I tell you, see, here we have written XAF, right? What is XAF inside the reactor? Same thing. And is it same thing throughout the reactor? Yes, because it is mixed flow. Then where is the more conversion or less conversion here? It is only one conversion, steady state conversion. Even CAF is same. This we are talking about isothermal. Okay, yeah, I have to write here isothermal. Yeah, isothermal, right? So that is why temperature is same throughout anyway. Good, yeah. So that is why do you say that for in a mixed flow you will have you said less conversion, or you are not of the opinion to have less conversion, because many students will think that mixing is good for reaction. It is not good for reaction. Why? Mixing always dilutes the concentrations. When you have dilution of concentration, except negative order reactions, and we do not find them many in the nature. So negative order means okay, first order if I take negative order -1, minus Ra equal to K by Ca. You put 0 concentration, you get infinite rate. Excellent. How do you maintain 0 concentration? Yeah, I mean theoretically that is very good, no? But negative order reactions you do not see in nature. Okay, this is greater than 0, only 0 plus. Okay, so that is why, I mean most of the things, but in under some conditions you get also negative order, but that negative order comes only when you have the I asked also a question, Haugen-Watson models, right? Haugen-Watson models, I also asked you a question, what is the information you get from Haugen and Watson models? Haugen and Watson models will give you only rate expression for heterogeneous catalytic reactions. So under certain conditions of that complicated equation, when you are simplifying terms, when you are removing terms, some terms, how are you removing some terms? When I have 100 maybe partial pressure of A and 1 partial pressure of B, and in the denominator again you may have another 20 partial pressure of C. So like that, when you have this one we can remove. Some people may remove even 10, because okay, it's okay, I mean it's not, when I put 90, the 10 also I can remove. So when you are simplifying, under some conditions you will get some constant divided by partial pressure or concentration of some component, that becomes negative. We do not have many. So that is why we only have positive orders greater than 0. Then under those conditions you will have definitely a mixed flow reactor giving low conversions, because now you come to packets. One packet has come here, immediately you added that 100 packets, continuously you are adding. So one packet has come here very quickly. What is the conversion in that packet? Very quickly, instantaneously it came out, very less. So that means, are we using that concentration? Are we using that concentration? We are not able to, right? So quickly it comes out. So that means in that there is no conversion, and I may have another particle coming, the mean residence time is only 10 minutes, let us say, and the particle is coming, the packet is coming after 100 minutes. What will be the conversion there? Okay, 100%. But after 100% is converted, what is this fellow doing inside? it's waste, no? See, it's a dead space in fact there. That fellow has to come out and fresh fellow has to come for the reaction to take place. What you see here is instantaneous mixing, and when I look at this reactor, I will see the concentration, the pockets which have stayed 1 second, 2 seconds, 5 seconds, 100 seconds, 200 seconds. Imagine packets. Now, okay. So, now that means in the packet where 1 minute back it entered, conversion may be only 1%. The packet which has entered 100 minutes back, because it may be there still, because till infinity it has to come, the conversion is 100%. The average of that, now remove the packets and then just imagine molecules. So, what you see is the average composition of all these pockets, and these pockets are there because of mixing with various times, different times. What you see at the outlet is, which you cannot see with the naked eye, is a composition average of all these pockets with different times. You look at the reactor, you will have again 0 to infinite distribution. Why? That is the definition of perfect mixing. I measured here 0 to infinity, but even if I look at inside, because this is true reflection of inside, also I will find out pockets with 0 to infinite residence time distribution. So, then in the particle which has entered just 1 minute back, conversion may be 10%, in another one 50%, another one 40%, another one 60%, average of all that is coming here. That is what you see. On the other hand, 1 second, I think will come. On the other hand, you have the plug flow. In plug flow, okay, all these, all these pockets, again 100 I just introduced, all these pockets are coming, absolutely we are not allowing any axial mixing or any disturbance, all of them will be coming here. What is the conversion of all the pockets here? If you define 100%, that is 100% conversion, or if it is 90%, the it is 90% conversion in each and every packet. So, now I break all the packets and then mix them, it is same. Whereas here, if I break them and then see, I have 20%, 30%, 50%, 40%, 100%, average of that is definitely smaller than this. No doubt.
So then is it possible to define an ideal residence time distribution?
This itself is ideal residence time distribution, because we are mixing ideal, perfect mixing and ideal reactor.
We are assuming that it will come in this way.
Not assuming, we can mathematically prove.
For example, say that
We are not assuming here, mathematically we can prove precise. It is exponential decay.
say for example, so we have say for example 100 particles coming in, say 100 molecules, molecule number 1, 2, 3, we number them, and like it's not practically possible, but let's assume for a moment that.
That's why we said pockets, because one molecule you cannot say conversion. So, there should be a group of molecules. That's why we are saying it is conversion, right? Yeah.
So my question is, for example, if we are getting 100 packets, we let us number them as 1 to 100, and when we let us after some time, let us check the outlet. The packet number 1 comes, then 2 comes, then 3 comes, then 4 comes. It's not possible.
No.
It is not possible. But if we
See, when it is not possible, we do not have to discuss that. No, when it is not possible, because here I collect, let us say, small amount of liquid, right. So, now when I look into that, if my packets are able to identify, when I am identifying, I will see packet with 1 minute mean residence time, 2 minutes, 5 minutes, 6 minutes, 100 minutes, all that. Now, 100 minutes 100% conversion, 5 minutes 40% conversion, another 60% conversion, all that average only I am seeing at the outlet.
But what I said, sir, if the packets like 1, 2, 3, if they came out in the order in which they came.
No, you are imagining that these packets are coming, one is coming first, afterwards another one is coming, afterwards. No.
If it came like that, it would be an ideal.
When I take a sample of some amount of liquid, in that liquid itself I will see all my packets with different ages, and average of that, and now different ages means different conversions. All those conversions I then mix them and then see that. That is what you are seeing when you are measuring it at molecular level. Okay. So, then what you see here is a low conversion, because you are now mixing the packets with 100% conversion, that means 0 concentration of reactant. Okay? With with 1 minute packet where the concentration is, if I have 10 moles per liter, that may be 9 moles per liter. That means 1% conversion, sorry, 10% conversion, right. So, these things I am mixing, right. Abdul, what I say at any time here is a mosaic of all residence times, theoretically speaking 0 to infinite residence times. And when I have these pockets with 0 to infinite residence time, the conversions or concentrations in each pocket is different. I am now putting all of them together and then trying to get an average concentration. That concentration will be definitely, I mean, if you are talking about product, it is more than the concentration of product. Okay, conversion let us take. That conversion is definitely less than the conversion in plug flow. That is the reason why without even equations, we can say that why the concentration, the conversion in a plug flow reactor is higher than conversion in a mixed flow. What you have to remember is that it is not instantaneous reaction. When continuously when you are putting some fresh reactant that goes here, it is already having some concentration CAF outside. Because of perfect mixing, and the CAF also is coming because of average of all those packets. You are talking about steady state, that means steady state has reached somewhere already earlier. We are talking about steady state only. If it is unsteady state, then we have to also see how concentration, one can find out, that is not a problem. Okay. We are talking about steady state where CAF is already established here by the combination of pockets with different concentrations, right. So, then when this is continuously entering, and that distribution of pockets, because no accumulation there, some 1 liter is entering, let us say in 1 second. In that 1 second, this 1 liter is coming out. In this 1 liter, if I see, I have 0 to infinite residence time distribution. So, in that various conversions, various concentrations. So, the average concentrations will be less. Same thing here, plug flow. I have here 1 liter entering, 1 liter coming out. So, when I take 1 liter here, when I see it, and then because of our ideal definition, that 1 liter only exactly comes here. So, what is the conversion in that 1 liter? 1 liter contains 100 packets, exactly same. Now, I am mixing them, I destroyed them and then mixing in terms of molecules. What is the concentration there or conversion there? Exactly same. So, you are not diluting, whereas in that case it is diluting. Please remember, I think Merit also was asking me, sir, it is instantaneous reaction in mixed flow. No. Okay, that average you are perfectly mixing, but that perfect mixing creates 0 to infinite residence time distribution, which comes at the outlet, and by definition outlet equal to outlet conditions must reflect inside the reactor. The distribution here also exactly 0 to 100%, I am sorry, 0 to infinite distribution. So, then the conversion here and conversion here is exactly same. Pooja, you are asking some doubt?
I got this point. PFR is having more conversion than CSR.
Very good.
But the point is the outlet CF is CF. How can it be equal to inside CF? Because one packet is coming out, so it have a distribution.
Okay.
10%, 20%, 30%, and one packet is residing in that container for more time period. So it have 30%, 40%. So there is difference in CF in outside and inside.
No. What is the definition? I think you have to do this experiment in your room. You have taps there inside? No. Maybe I think you have the bathroom taps. No. Take a glass. Okay. Allow the water to flow into the tap water into that, and then let it overflow. You call Danya or someone and then ask, take a pencil, stirring. Okay. Then add 1 drop of ink, right. Just see whether you are getting same color inside and same color outside when it is overflowing. Yeah. So, then why do you say that CAF is different here, CAF is different here? It is exactly, that is what is perfect mixing definition. No, the combination of all that, because of mixing that 0 to infinite residence time distribution, which gives you some average concentration, that is reflecting here. Because this is a continuous reactor where whatever is coming here, it has to overflow, it has come out, right. So, whatever is happening, you will have immediately coming out because of perfect mixing. You just imagine, you have the tank and then your glass tank where you have a very high stirring. I think if you go to our lab, I think maybe Nagarajan or Rahul will show you. We have a stir tank there, in that RTD experiment. You put one drop of ink and then show them. I think beautifully you can understand that. The moment you put that one drop of ink, if you allow good mixing there, the same concentration is reflected in the overflow pipe outlet. Okay. Then onwards, the color is decreasing in the tank, and also the color is decreasing in the outlet. That is why this concentration decreasing continuously. Okay. So beautifully we can imagine, it is not a problem at all for us.